I don't have this on your handout. This is on your PowerPoint. This is a new slide because I really wanted to make it critically significant.
You said it's not on anything we have?
Oh, it has on your, it's only your PowerPoint has this. Okay? Unless you loaded your PowerPoint from like a long time ago. You can't do that.
A long time ago, it's like a week ago.
It's not that long.
Well, I don't know. But anyway, there it is. It's on there now. If not,
Now you get to reload it.
I just,
What's this called? Primary diagnosis of acid-base disturbance?
no, it's called, yeah. I like to call it that sometimes, right? And so, let's go back to that equation. I'm going to redraw this. Okay, and remember we did this at the beginning, clearly we're doing a lot now, and I had talked about, I played some things that you could tell, like if you have alkalosis, you know, you might be able to tell the difference between respiratory and metabolic because like CO2 levels or breathing and everything like that. But it was a little misleading, and this is where the real thing, this is the real deal. And it's going to be, you don't really have to memorize this, or you can, but you might mess it up. I'm going to show you how to figure this out. But the real thing is, if you're going in, and we're trying to figure out what's going on, you're going to have 3 things measured. Okay, at least this is what the book tells me. Okay, so real life you can tell me. But out of all this, we're going to measure CO2 levels. We're obviously going to measure pH, or hydrogen levels. But what I've ignored up till now is you will, this is important, measure
Bicarbonate.
bicarbonate. Now bicarbonate matters. Okay? I know it's bad for you because you're like freaked out, but bicarbonate matters now, okay? So draw a line, bicarbonate matters, okay? For this one. And don't look at the words right now, don't even look at the chart that much, except I'll tell you. But that's the key, okay? And as I go through this, we're going to see the following. In fact, I'm going to take that off. I'm going to look at this and just put it blank, and we're going to reproduce it. The key with this is the following. First of all, and you can see sort of as we see this, you know, once you determine that you have, you know, low pH or high hydrogen or high pH, low hydrogen, you know it's acidosis or alkalosis, right? That's an acidosis and alkalosis. Everybody agree with that?
Yeah.
Okay. The key is it respiratory or metabolic? And that's what you see we have CO2 levels and bicarbonate levels. Now, as I go through this is a hint for looking at that idea, is that when we do respiratory ones, like when the respiratory is the cause, what we did before with the law of mass action thing is going to like fit like right real easy. When we do metabolic, we're going to see, this is why I put it in red, there's going to be a little tweak to it because the respiratory system is so good at responding, it literally is going to sort of reverse the CO2 levels. And so we'll see that. But before we do that, here's a clue too, because you don't have to do everything I'm doing to get it. It's not an essay. But the one thing you can see is the following that will help you as you go. If you look at the CO2 and bicarbonate levels, what do you see?
They're high.
Well,
Oh, no.
they match. Okay? And we're looking at any condition that they're both low, they're both high, they're both high, they're both low. They go together. Okay, that helps. Believe me, when we're doing this. Because then you can kind of check. Again, I wouldn't necessarily memorize this. We're gonna show you how you figure it out. Boom. It's gone. It's gone, okay? So we're going to reproduce it. But I'm going to show you, and we'll do, again, for the people that say, we'll do every one of those. Every one of them and show you how it will make sense. Okay? So, let's, and we're reproducing the chart. So, again, we can put symptoms or whatever. And again, the first one's pretty easy too, right? And again, I don't know which way they did it here, but we'll do low pH.
Acidosis.
Okay, low pH, which is acidosis, which again is high hydrogen, right? You know, you have too much hydrogen, it's low pH. We already know this is acidosis. And then the other one is high pH. We know it's low hydrogen. And that is alkalosis. Okay. Okay, and I'm going to put respiratory and metabolic, respiratory and metabolic. And under here, let me just put these here. CO2, bicarbonate, for all of them, because that's what we're going to just say up or down. Okay? The ones that are the easiest, okay, are the respiratory ones. Because we're going to do the same thing we did early on with the law of mass action, and instead of ignoring bicarbonate, we're just going to include it. This is one that's going to make total sense, okay, if any of this makes total sense, right? And so, again, we can do respiratory, which means respiratory is causing it. So if we're on this side, we already know, we're used to this, okay? If respiratory is causing acidosis, what is it, hypo or hyperventilating?
Hypo.
Hypo, right? So we'll put this. So now all we're doing is the same thing, but we're going to see it's going to basically get all of these. So again, remember, in respiratory we're starting over here. So we hypoventilate, and so what's happening right now when you hypoventilate?
You're conserving.
Just follow the equation. Our CO2 is going up. Okay, you can actually put that here, right? 3. If your CO2 goes up, the law of mass action says, right?
Is this one where you did the balloon example?
Yeah.
And I didn't get it.
So don't forget the balloon example. But if you increase one of these, you're going to go that direction. Everybody agree? That's like old school. All right. And then if you do that, you do what? And by the way, what else do you do? Okay, we ignore this, but if you're basically going this direction, you're increasing both of these products. We just didn't say this before. Right? I mean, if you're going this way, both of them are going up. So if you're increasing hydrogen, which again, that's pH down, that's your acidosis, and it's respiratory. But you're also, again, you don't have to put it this way, you are also increasing bicarbonate. Which means, for respiratory acidosis, the arrows are up. It's exactly like we figured out before, that we hypoventilated, like we did at the beginning of the course. We hypoventilated, that means we built up CO2. And actually, right at that point, you're like, I know the other one, because what?
They match.
Bicarbonate match. Okay? So that's why, that really does make it easy, to do it. But to actually see how it works, we'll just follow it here. Because it's not going to be an essay, it's just going to be, I'll tell you the questions that they're going to be in a minute. But so you've increased CO2, you remember that we're doing law of mass action, going that way because we have too much. Both of these goes up, and that means we have acidosis, but also bicarbonate's up, and that's why if you look back over when we fill this chart, you're going to come back and you're going to see that respiratory acidosis, obviously we have high hydrogen, that's acidosis, you're going to see high CO2, high bicarbonate. You have a patient that has those, you're like, we obviously has acidosis, we know it's respiratory.
Sorry, you're saying I know you're just kind of going through one part of the chart and then starting over here.
Yeah.
But you're saying that that's the cause is respiratory.
Right, and that's why you're going to know the patient has acidosis alkalosis because you just take the pH. And you're trying to figure out, was the respiratory the cause, or was it metabolic that was the cause? And by looking at these, actually all three obviously, but really looking at these, you can determine whether it's respiratory or metabolic. You've already determined it's acidosis by just taking the pH. And now you're like, okay, which one is it? If you have both of these up, based on where we're going, you're going to know it's respiratory. Before we do metabolic, because remember, metabolic is more confusing, let's just do the other one. Okay? Let's do hyperventilate, because we're doing the respiratory problems. We hyperventilate. Okay? Which means what? Decrease CO2. And we already know the answer then, right? Before we even do it. For respiratory, we decrease CO2, so therefore decrease bicarbonate because they go together. But just for fun, let's go and just make sure it's going to make some sense to us. If we decrease CO2, law of mass action says So, that means you decrease hydrogen, pH goes up. We've had, that's called respiratory alkalosis. Okay, but also what happened? Because both of those decreased. So you did it, it worked out both directions. Okay, so you decrease carbon dioxide because you breathe it out. Law of mass action shift this way. That means both of these have decreased to do that, and boom, we have the answer. Remember, you don't have to do it that way. Okay, and again, you can do it to. I would kind of understand it in case, because if you just sort of memorize it, I think you can mess yourself up. So you sort of want some sort of clue when you start. But basically, when you look at that, they make total sense as far as doing the law of mass action. All we didn't do before at the beginning of the course was add bicarbonate, but these are going to do the same thing. The real key is, again, that these are matching. Okay? Does everybody sort of get that? Okay. For the metabolic ones, here is the difference. Okay? For the metabolic ones, the following. We have that equation. And so remember, for anything metabolically that's starting in, we're going to start over here, and the respiratory is going to respond. So let's do one. And we can vomit if you want. One more time. Okay? So, I don't want. We vomit. Okay, and this is an important point. This will help us, and actually you'll have it done right away. When we vomit, what did we say? We lost hydrogen.
So that means we lost bicarbonate?
That means the opposite. Okay, and that's the key to this. You put in parentheses that basically, because we're starting this. And the idea sort of is, and this is a little abstract, but it's really important, is the idea that, normally these things are at a certain balance because bicarbonate acts as a buffer. If you have too much hydrogen, it picks it up. Now, if you lose hydrogen, it's like you have too much bicarbonate, or you could actually do it by increasing bicarbonate. So in parentheses, you want to put the idea that when you're talking about, well, first of all, when you're talking about lower hydrogen, and caused by something, it is called metabolic alkalosis. But in parentheses, it's also associated with an increase in bicarbonate. So all you've got to do is remember, we're used to this kind of up-down things like oxygen, CO2. All you have to do is remember that, okay? That if you're, because remember on this side for metabolic, that anything that you're decreasing hydrogen, effectively you are increasing bicarbonate, okay? And again, I don't want to go much beyond that, even though it's, bicarbonate levels are really important. But if you remember that, then you'll see how it works. First of all, you already know the answer, okay, of that. But let's follow this, what's going to happen. Okay, so now, you have that in parentheses, right? But now we play the same game. If you, with kind of ignoring that decrease. If we did before, if we decreased hydrogen, just look at this again like we did before. The law of mass action says, okay, so we decrease hydrogen, again, that's metabolic alkalosis. So we're going to shift to that way. And what happens over here then? Erase all these anyway. If we're shifting this way, what happens to CO2 levels?
It increases.
Wait a second, we're going that way, right?
Yeah.
So CO2 levels are decreasing, right?
That's all right.
That's how we did it. We did it before. We lost hydrogen by vomiting. Law of mass action took us this way. That means CO2 decreased. And in response to CO2 decreasing, what happens? Who responds? Metabolically caused it, who's going to respond?
Respiratory.
Respiratory. And respiratory is going to do what?
It's going to decrease.
So we're going to hold our breath. We're going to decrease respiration. And that means we're doing what to CO2 as we're decreasing respiration?
You're increasing it.
Right, and that's the key for metabolic. The response is so good that what you actually measure will be, because of this response, the opposite of what we did here. So you have high CO2 because of that response. Okay, so we do all this, and that caused we lowered CO2 like we said, but the respiratory says, okay, I'm going to take care of it right away, and actually holds it to it so it overcompensates, so you actually have higher CO2. And of course, we knew it was going to be that answer from this, right? As long as you remember that, because we knew CO2 goes. But the idea why it's harder, and this is why when you look at this a second, I actually put it in red, because this is, which one is this? This was metabolic alkalosis, right? And we have what? Up and up. Okay. This is why the way we did it here is I put it in red, because the idea is the respiratory response is going to reverse the CO2 basically than what we expect. So even though here we did it where CO2 was lower, we did it, the fact is the respiratory responded so much that it actually then increased CO2.
So that will be the result.
That's a result. That's what you measure, patient-wise. So that's why, and again, this is to help us understand, but of course, as long as you got that right away and you remember that they're the same, you got it, right? I mean, I'm not going to make you work this out. I just wanted to sort of show you how you might be able to use this instead of trying to memorize it and not mess that up. So it's like for metabolic alkalosis, you have it right there, right? As long as you remember that instead of just dealing with the hydrogen, the bicarbonate's opposite. If we do the again, even if you just write this, without even going through it, if you have metabolic acidosis, okay, your hydrogen is what?
It's a lot. It's increased.
So your bicarbonate is?
Also decreased.
Okay, so we have, and then if our bicarbonate decreased, what else is decreased?
CO2.
You've got the answer right there. Okay, you don't have to work it all out for that. So where are we here? We're on metabolic, and we have what? Down, down. Right. And low, low. So you can see we have reproduced this. You can, and I'll tell you the two type of questions we're going to have. You can memorize this, but I would use some of this to make sure you don't mess it up, because you can always mess this up if you're memorizing. If you somehow use this to make sense, it's fine. So I will have two types of questions, probably two questions, two multiple choice questions. I can do the following. I can put it over here, and that's all the material. As far as there's no new material that we're covering. This is the end of it, and then
So then it's review on Monday.
yeah, just review on Monday. So, but here's the key. I can give you this. You have high hydrogen, high bicarbonate, high CO2. ABCT. What is the condition? Respiratory acidosis, respiratory alkalosis, metabolic acidosis, metabolic alkalosis. Whatever, it's obviously one of those four. So again, one way or the other, you've got this information here, whether you rewrite it or you do it. But that will be one of the questions. Again, what's the answer here?
Acidosis.
Yes.
Okay.
Okay. So, again, if you just memorize it, it could be a mess, okay? You could try to memorize it, but I would find some sort of clues here to make sure you're right. Okay, you don't have to write all this, but whatever works for you. Now, the other idea would be that you have, metabolic alkalosis.
And then you're going to ask the levels.
Yeah, and I'll have up, up, down, down, and you have to figure out which A, B, C, D, which is the right one, right? And so obviously the right one for metabolic, if I do alkalosis, would be low hydrogen, high CO2, high bicarbonate, choice C, or whatever it is. So, two questions will be on it. And the reason, again, the reason I put this in is I didn't want to be misleading. I want something clinical, versus at the beginning I kind of said, well, it's your breathing, but really, this is the real deal, unless they change it on me, right? That this is sort of how they diagnose. Basically, looking at this. Yeah.
I feel like your body works to maintain its own homeostasis without you controlling it. So I was always kind of confused from the beginning of the semester of why you're saying hold your breath, what you.
Well, you're not holding your breath. You're decreasing respiration.
Right, but I meant so your body just naturally is just not breathing as much.
Well, you're in homeostasis.
Right.
And everything, that's what I mean. Everything's at a certain balance, and then as things change, you you keep compensating.
Right.
Just like our blood pressure, right?
Right.
You're constantly changing that. And the key is, especially for the respiratory system, remember, it's our CO2 levels, hydrogen, that really is our central controller in the brain. And yeah, as CO2, if you start holding, let's say you start holding your breath, that CO2 is going to trigger, increased respiration. But if you hold too long, it's also signaling, acidosis, and then we kind of go in. So
Yeah, so I know it's always going back and forth, but I guess I just still kind of confused with how your body does it. I mean, it's going to be doing on its own, but say you vomit and you're vomiting out all your acid,
right.
and you want to get it back, so you're decreasing respiration. What is your body literally doing? Making you breathe less?
Yes.
Okay, like.
It's literally because if you go back to what we learned as far as the central the chemoreceptors for respiration, remember it's responding to CO2 and acid levels, right? CO2 comes in, gets rid of acid, and as acid's building up, it naturally will signal increased diaphragm, increased respiration.
Right.
Automatically.
Yeah.
We have some control of respiration, right? But there's some that will be automatic, and that will be automatic.
Right.
Okay.
So if you're feeling nauseous and you need to vomit, should you just hold your breath and it'll go away?
No. You can try it.
What would happen? If that's what it wants anyways.
No, it doesn't. It doesn't want that until you do it. Okay. That's going to be a response to your loss. Okay. That won't work. Okay. Sorry. Try to avoid vomiting. Well, go ahead.
Just random question. If you're hyperventilating, does that mean your body's like reabsorbing water too? Is it like the same eliminate pollution on that side as it on the right?
Yeah. We don't deal much with water on that. Yeah. Does it reabsorb water?
Yeah.
You mean like in the kidney? If you're losing water, you mean?
Well, like you know how when we're lowering like the H plus, we're raising the bicarbonate. So I'm wondering if you lower the CO2, does that mean you're just ignoring water right now? But does that mean you're actually losing water?
I don't think so. If anything, these will sort of go together, but I don't really know the answer. Because everybody ignores water. I don't really know for this equation the effect of water is doing it. Simply do not know. We've got this.
I was just wondering, like, when you first started the second section, when you were talking about the intercalated cells versus the primary cells, is it important to know, like, is that just where they are in the,
Yeah.
are the intercalated cells right at the end of the distal tube, and the principal is like the corner of the cluster?
Yeah, I mean, it's just, it's that area. I think they're actually, if you go to the end of the distal tube, top of the collecting duct, they're sort of all interspersed there.
Right.
And that's all you need to know.
And it just, the difference between the two is just because of how they respond to, like, what the proteins are in them as well.
Yeah, it's, again, we're dealing with membrane proteins. We're dealing with transport proteins more than what's in it, right? And those are the ones which are transporting these things back and forth. And the chapter we skipped, chapter 5 to the end of it, talked more about these transport proteins, specifically. And that's sort of why we have this tiny black hole that you kept kind of bringing to, but we didn't have time. Okay, you guys have so many questions. No, plus the holidays sort of really freaked us out too. It was all kind of crazy. We've had a lot of holidays. Is everybody ready to get an A on this test?
Yeah.
Yeah. Yeah. Oh yeah, I'm worried about you. I don't know if I can get over 100 this time. No, I'm just kidding. Yes.
Could we do one of that practice problems on your?
Sure. Yeah, let's get ahead of it.
Um,
You want to do that bronchial one, the hard one?
yes.
Okay. Yeah, I have one hard, and there's going to be a question just like that on the test. Okay, slightly tweaked around, and so let's put this up and show you how to do this. Thanks for moving up. Okay, at least you're like way back there. Okay, and you're still back there. You're going to stay there, right? Okay, I know we got lots of room. Okay. All right. So let me find. See if I can find this, just so I show everybody that question. I think this is the right one. No. You can see my desktop is like, I got a lot of kidney stuff.
No.
Hang on. Say no?
No more stones.
No, I'm not putting the kidney stuff. Oh, you saw those right last time, right? Those were nasty. Where is this stupid thing? Okay. It's not these. Just be patient with me. Driving me nuts.
Are you just looking for your actual practice problem?
Yeah.
Oh, we don't have access here.
I don't have like internet here. It's on my desktop somewhere. I have like a billion things on my desktop. I'm trying to think what I named it. Wow, what's going on with this? How am I out? What? My whole computer's freaked out here. Why is this not working? Okay.
Is that one of this one? The guy. This one is this one. This one is the conditions. Remember,
Okay. Okay, so look at this problem. And there's going to be something similar. Now we're back to the respiratory. We're back to chapter 17. And to do this problem, we need a couple things. Well, first of all, just read this problem and you can see how crazy it is. And then I'll show you how to do it. Okay? A drug was specifically applied to a portion of the lung bronchioles. Now, it was observed that the pulmonary arterioles constricted as they passed through that region. Okay? And then, which of the following statements are false, and more than one may be circled? Basically, I just want you to go through each of these and figure out what's true or false to practice. And the real question is just going to be one answer type thing. But, so we've got two things here. And literally, if you kind of look at it first, you have this idea that you want to be thinking about this, and we're going to review how we did this before. If you sort of remember from chapter 17, and I can review it, we had that sort of hard thing where we talked about that we could have bronchioles of different oxygen concentrations. Let's say that's low O2 and high O2. And we had these pulmonary arterioles that pass by these, that respond to the oxygen levels and CO2 levels, right, basically. And the idea that was, well, let's see if we remember. If we had lower CO2, for whatever reason, low oxygen here, okay, and this is oxygen. If we have low oxygen, what was going to happen to these arterioles? Were they going to constrict or dilate? Constrict, because our job is to pick up oxygen. Correct? So, we already know, if you read this, you just read it right here. A drug was specifically applied to a portion of the lung bronchioles, so we're applying a drug here. Okay? It's noticed that the pulmonary arterioles passing through it basically have constricted. So we know whatever we did to this, well, what did we do to this? Okay? If this constricted, that means the oxygen levels are low. So what the drug applied to this must have done what to this? Well, that would be high O2.
Right, but aren't you talking about the bronchioles?
What we're saying the drug was applied to the bronchioles. It did something. But we know what it did, we can reason it because as these arterioles passed through, they constricted. That means whatever we did lowered the amount of O2. Okay? Because these constricted. If what we did raised the O2, they would dilate. So the drug was applied to the bronchioles and basically lowered the O2, which means what did it do to those bronchioles? the drug had to have caused bronchoconstriction. Because the only way the pulmonary arteries are going to constrict going around it is if this lowered the O2. The drug had to have constricted that lowered the O2, and therefore this constricted as well. That's what the information is saying. Okay? Now we got to go for the answers. But is everyone sort of, again, this is a hard question, but that's why I put it on here, okay, and people are going over it. So, but that's sort of, you follow language you get. We're applying the drug to the bronchioles. So this is unknown drug. And we noticed after we did that, that the pulmonary arteries constricted. Okay? Which means whatever we did had to have lowered O2, and that therefore, basically, we kind of know that whatever that drug was must have constricted the bronchioles so that there's less oxygen now in that. And in response to that, these pulmonary arterioles constricted because we don't want to waste our time. So whatever drug it was caused bronchoconstriction. Yes?
Like I thought, like if I understand, like one's a pickup and one's like delivery.
Yes.
So I thought like
This one's a pickup, right?
The pulmonary arteries are pickup.
right. So it's
This is delivery. The bronchioles are delivery, right?
so it's what is it delivery?
Well, normally what? If it's open, it's delivering oxygen and getting rid of CO2. But we applied a drug to that. And if that drug constricted it, doesn't that mean we don't have as much O2? If we were doing it before, just separately, we said that, again, if you had low O2, originally, this was going to dilate to deliver more. This is, the bronchioles are controlling oxygen. If we constrict this, there's less oxygen. We applied a drug that constricted it, caused less oxygen. So the first thing they did was drug, caused bronchoconstriction, therefore less oxygen, and therefore as the pulmonary arterioles went by, they said, nah, because there's not enough oxygen. So this caused this responded to that.
And the other one dilated.
And the other one, yeah, other
It's
ones were
like
dilated,
more.
right, because we didn't apply the drug to that. So we applied a drug that caused bronchoconstriction, and therefore that means now, because we constricted, there's low O2 there, and because of the low O2, the pulmonary arterioles were going to constrict it. We reasoned that out from that. We applied the drug, just because all we knew from this, we applied a drug, all we knew from that is that as the arterial passed, it constricted. From what we knew before, that means this has to have low O2. That's why it constricted. We don't get this?
Well, no,
No,
like
what- So,
no, go ahead.
I was gonna say, yeah, but what's the next step? Like, after that.
Yeah. Well,
Therefore what?
therefore we're going to figure out what the drug was. We're going to go through each of those answers
Okay, I
and see
think
which
I'm
one's
just not
true.
understanding how the drug works because like in the slide it was always saying like low O2 means that bronchial dilate.
Sure, but we applied a drug.
Okay.
Remember, drugs cause something.
Right.
If we applied a drug and it constricted, boom, we overrode what it's supposed to do. The drug caused constriction, and therefore this has lower O2. That's what the drug did.
So is it acting like an antagonist?
We're gonna get to that because we're gonna figure out the answer. Okay, we'll see what the possibilities are. But the idea, do you see? What don't you see?
I don't know. I guess because we never talked about drugs, like just
Of course, this is critical thinking. This is why we're doing this. The idea is that without the drugs, if you just said, if we just gave one that we were asking, if we said a pulmonary arteriole constricted next to one of these alveoli, we would know it's low O2 from what we did.
right.
Okay. And now I'm saying, so we know that. We know it has to be that, because that's what I said. This constricted low O2. Now the fact that we applied a drug to the bronchioles means we did one of two things to the bronchioles. We dilated them or constricted them. What would cause low O2? Constriction. If we dilated them, boom, we'd have more O2, and this would open up. So does that start to make sense?
Yeah.
Okay? It's not easy, but it should
Well,
start to
I
make
mean, like, I
sense.
understand what you're saying, it's just before we were thinking about it more on its delivery, like, if you
Sure,
open it up, then,
yeah, but now we're not.
okay.
Now we're applying drugs to it and seeing the effects.
Okay.
Okay? So, but does everyone get that before we move on?
So how do we know where to start with?
Well,
From bronchitis?
because this. We start because if we said that we applied a drug to this, okay, we don't know what the drug was, but we know this. We just said that after we applied the drug, that this constricted. That means, based on what we know before, that means this has to have lower oxygen, right? It dilates to where there's more oxygen, it constricts to where it's low. The drug must have resulted in low O2, or else this would have constricted. We apply the drug, all we know is that this constricted, therefore we know that this has low O2, or else why would it constrict? Yes? And then basically, we can know, I mean, again, you've got a choice. If this drug dilates, we would have more. It has to be causing bronchoconstriction. And if you have cause bronchoconstriction, that means, you know, because we put this drug on, you know, or it could be, you know, just think about histamine, okay? If histamine is going to cause constriction, you're going to have less O2 there. It's not that good, but we're not going to waste our time trying to pick it up. We're going to go somewhere else, and that could be one of the possibilities. But that's where we start. Okay? Does everyone sort of get that? You know, because, you know, you remember, if it were just a normal test question, you know, if you just look at the normal test question, we had low O2 and high O2, and we had these pulmonary arterioles, and we said, because its job is to do what? Pick up, that if it had low O2, what would it do here? Constrict. If it had high O2, it dilates. I just said, what? That whatever that drug was, it caused constriction next to it.
So they have low.
So you have low O2. Okay? And so you figured out the drug caused low O2, and so clearly the drug couldn't have dilated or it would have caused more O2. It had to have constricted it. Okay. Now, here, and that's it. But you've got to figure out the answers, because that's the idea of what this could be and what it couldn't be. Okay? Now, the key with this is two things. That if you have low O2, you know, the chart has low O2, high O2, low CO2, high CO2. If you have low O2, what does that mean for CO2? High CO2, right? They're always in opposition. Yes? All right. So you need to know that. Now, the other thing you need to know comes from chapter 17, and we're going to put it there. You know, we have, especially on the notes, not just on the PowerPoint, we did a whole slide on bronchodilation and bronchoconstriction. So this is really just repeating your notes. You got to know that because you can see I'm using muscarinic and beta 2 and all that. So we've got to remember bronchodilation. What caused bronchodilation? Epinephrine. Remember, sympathetic doesn't come here. Norepi's resting because it did all that cardio stuff. But adrenal epinephrine does. And so epinephrine causes dilation. And it's doing it by doing what? Binding to beta 2 receptors. So, beta 2 antagonist, beta 2 agonist you're thinking about. Okay, that's that. Now, for bronchoconstriction, we had what? Two major things. Parasympathetic, they do innervate. And remember, parasympathetic is rest, so you know we're going to constrict. We don't need as much air. And what was the neurotransmitter? Binding to muscarinic receptors. Okay. And what was the other one? Histamine. And it just binds to histamine receptors. Okay. With that information, we can answer the question, or anything I can give as far as that, because basically, if you just look at this a second, okay. First of all, we already know we caused what from that other one? Bronchoconstriction. So we got two ways to go here. We do what to dilation? To cause constriction. Reverse it, antagonist. Okay? If we want to cause bronchoconstriction, we do agonist or the same thing. That's the two, remember, that's the two ways to go. So now we look at this and we look at the answer. Remember, when we're doing this, if there's two parts, they both have to be true or false. And so let's look at the first one. Could this reagent be a beta-2 antagonist?
Yes.
Yes, right? Because beta-2 normally dilates. If you put an antagonist, it's going to constrict. Okay? The second part of that, will that result in decreased levels of carbon dioxide?
No, increase.
Increase. Nah. Okay, so that's why that's wrong. Does everybody see that? Half right, half wrong. So wrong. Okay, that's why you need to know that. The second one, could this have been a muscarinic receptor agonist?
Yes.
Yes. Okay, its agonist does the same thing. When acetylcholine binds, it causes bronchoconstriction. Okay, would that result in a decreased levels of oxygen?
Yes.
Yes. Yes, yes.
It says it too. I mean. in the
Well,
question,
it's got, but we're
right?
saying, is this answer true or false? Oh, yeah, you're right, it says it there. So in fact, the next one's real easy.
Yeah.
The third one is like the class that you wanted to take, okay? The third one is like, did minor cause bronchoconstriction of the secreted region? Yes, okay? That was, the good one, okay? Okay, if an application of histamine, would that reverse the effect?
No.
And make it worse? What would you need?
Any
Histamine antagonist, okay? And so, what would, okay. So, that's how to do that kind of question. Because there's going to be a question just like that, but I'm going to tweak these so I don't remember which one, it's like which one is true or which one is false. We're not going to have to kind of do this.
because that one's false.
Well,
Inside.
which of the following statements are false? So, this one is false. A is false. What was B? True. What was C? True. What was D? False. Okay, this won't be like a real question. I'm not going to make it like that. It's going to be like this, but I'm only going to make one true or one false, whichever I decide.
Well,
But in
if this was, it'd be A.
yeah, A and D would be false, exactly. Okay.
Yeah, and the reason D is false, you're just saying, like, if you added histamine, it's an agonist, so it would increase the effect.
Yeah.
Not. the
That,
reverse.
right, and so that's why you would give, and part of some of the drugs, either you give something like epinephrine or a beta-2 agonist, okay, if you have like an asthma attack, or you can also give, either a histamine, usually I think you do a histamine antagonist, okay, for an allergic reaction. You're producing histamine, closing it up. If you give an antagonist to that, it will help reverse the effect. And so that's a hard question, yes? Yes. That's why do I put extra questions? Why do I have people do this? So that we figure out how to reason it. And again, this question is on the test, except I'll tweak the answers a little bit. But this is the information to do it. So you're almost done with me. A month from now, it's like, what was that about? Okay, it would be literally, forget, okay? One more month of me, and you are like done with this computer class, I hope. No, you are done. Otherwise, I'll see you next semester. No, actually what will happen is Stu will have a line of about 100 people trying to crash this class. Okay? But I recommend Stu. So any student, again, he teaches days here. He's such a good teacher. Every day is fun. Okay, I'm like horrible compared to him. He's so much fun. He's really a cool teacher. I don't know what else to say. He's my fave. Anyway, that's that question. Whoever asked. It was one of you guys, right? It was you. Okay, did it help?
Yes.
That's the hardest.
I got it.
Now,
Thanks.
again, while we're up here too, okay, just a glance if you haven't looked at these. The first page, practice the hemoglobin saturation curve stuff. List the steps of oxygen carbon dioxide transport. It's not even an essay, just practice. Okay. Talk about how the kidney works. Then here's the page question in which I kind of have you play with what we did. Which ones of these could cause hypokalemia. I basically just have you take these different things and work things out. But look at this next page. Okay, this is what it's going to be like on the test. I'll start with one and take you through it. Now remember, this is a good, since you're here too, if I'm saying, and I don't have it up anymore, but if I say a defect, It's almost like turning it down, right? So, or reversing it like I did for aldosterone. So if you just even start out here, because I don't know if I want to do it, because I want you to do it, and come back on Monday. But just to start us out here, okay, you're going to have all this. Let's redraw this guy, type A. And again, well, let's just see. We got type A responds to what? So what's it going to reabsorb? What's it going to get rid of?
Hydrogen.
So it's going to reabsorb and potassium. Okay? Now, that's how it normally is going to work, right? If we have a defect, guess what we're going to do to it? We're turning it around. So we're going to reabsorb hydrogen. Remember, you
Wouldn't the
can,
defect be the opposite, like type B?
well, I mean, effectively, it's going to end up being that. The idea is, this is normally, well, let's put type B and let's see.
Can we just move on to type B if it's
Let's just
defect?
calm down. We're not moving on. We want to see what happened here. Okay, we're not moving. We're not moving on. We're not moving on. Okay, because we're looking. This is going to be the defect right here. I mean, we can put type B for fun.
Type B is what a type A defect, right?
Okay, let's just calm down a minute. Okay.
Okay.
I mean, my brain is like, wait, I'm going to hang it in here myself. I want to like draw this and just sort of make sure I'm not going to say anything wrong too. Type B responds to alkalosis by reabsorbing. I mean, effectively, it's going to have the same reaction, but so HCl3 minus and potassium. So it depends on how you want to look at it. Okay, the idea is that the only reason I don't, the end result is the same, right? Because what I'm saying is reversing this, and that is type B. So you're not wrong in that. But the idea is that this is basically, instead of doing its normal amount, it has stopped doing it, and so we're tending to accumulate the other, versus this is reacting to something. So, I don't know, but it's like a little point. If your brain does it that way, it doesn't matter. Because all you have to know is what would happen, okay? So what will happen if there's a defect in this? Okay, and the choices are, is that going to cause respiratory acidosis, alkalosis, metabolic acidosis, or alkalosis? And you can answer it either way. What's going to cause? No, remember, respiratory is if it causes the problem, which means hypo or hyperventilation. You rule those out right away. The problem is metabolically, right?
Because they're in your kidney?
Yeah.
Yeah, well, no, I was just wondering.
Yeah.
that's what I was
So
wondering.
the only time you're going to say respiratory acidosis, alkalosis is hypo or hyperventilation, basically, right? That's everything else is metabolic. And so this is going to cause one of the two. And what's it going to cause?
Acid.
You just look up here. You actually, if you said this would do it, or you reverse this, you're going to basically reabsorb hydrogen. If this isn't working, we're saying this isn't working, right? This is how it normally works, getting rid of acid. It's not working, therefore it's going to be
Metabolic acidosis.
taking it in, and we call that
Metabolic acidosis.
metabolic acidosis. We're doing the opposite. If it's a defect, you're doing the opposite. Just like with the aldosterone. Okay? I thought you would get it because you're like, okay, it
Well,
would be.
type B is alkalosis. Oh, wait. No, but if we're saying it's type B,
We're
type
not.
B
We are
is-
saying type A isn't working. Okay? What is type A normally doing? What is it normally doing?
responds to metabolic acidosis.
Okay, and it's doing what normally?
Secreting hydrogen,
Okay, so if it's not doing that, instead of secreting it, what are we going to be doing to it?
reabsorbing
Which
it.
is going to cause, if you reabsorb hydrogen, it is too much hydrogen, acidosis.
So the interrelated cells always respond to metabolic. That's what I'm conditions.
Sure. But this time it's causing it. But yeah, the kidney always responds, to any sort of pH imbalance. Okay. Now in this case, we're actually showing you, which is rare, well not rare, but in this problem, that we actually have the kidney has actually caused the problem. Okay. So this is, instead of vomiting or something else going on, this actually is causing the problem. Where these type A aren't, and again, you can think of it in the other way too. If type A are not responding to acidosis, you're going to end up having acidosis, right? You don't have a response to it. Or if you look at it this way again, you've got to realize that if this is normal and it's not working, then it's reversed. You're not getting, this is saying we normally have a given amount of activity in which we're getting rid of amount of, or blood, or stuff's going through, we're getting the right amount of hydrogen. If it's not working, we're not getting rid of enough hydrogen. That means we're taking it in, and that's acidosis.
I thought that getting rid of hydrogen was acidosis.
Hydrogen is acidosis. If you have acidosis, you want to get rid of it. Too much hydrogen is acidosis. Does everybody else see that?
So, in the intercalated cells then, for type A, when it responds to acidosis, means what?
It means what? It means this.
It's when it's getting rid of hydrogen.
Right. When it's working, it's getting rid of hydrogen. If it's not working, it's not. And therefore, you'll have acidosis.
But how come when it's not working for type B,
We're not doing type B.
we're saying type A?
Yeah. But your type B will be something different.
To switch things up a bit, could you potentially ask, like, could a defect in the principal cell result in high blood pressure? And like, go way across the board?
No. A defect will, because remember, you go, a defect in the principal cells will
Does it not
cause,
switch it?
will cause low blood, it switches, it will cause low blood pressure.
But wouldn't the defect then lower aldosterone?
The- But the defect, if you do, let's put aldosterone up here too. Got this? Sodium, and of course water. This is when they're working, and then we have potassium being excreted. Okay, and you're starting off with what? A defect in the principal cells. Okay. Well, what does that mean? That means it can't respond to aldosterone. Okay. Yeah. So then I think it would just work the same.
That's not it.
Did you were trying to get in? Do you have a question?
I think I might understand where the confusion lies with the
Yeah, but not
hydrogen
that.
and acidosis thing. Maybe you're thinking about when you're breathing out hydrogen, it's acidosis, but that's because you have too much.
She's trying to help you actually.
I got it.
Oh, yeah.
But, no, but continue.
Oh, so like in respiratory acidosis, for example, you are getting rid of hydrogen because you have too much inside of you. And the same concept of this is that you're taking too much hydrogen in. It's still too much inside of you, so it's acidosis. Maybe that helps at all. Maybe it doesn't. So never mind.
The fact that he said that we're dealing with just type A was enough for me.
Oh, okay.
Just because I thought
And remember,
that type B was the reverse of type A, but it wasn't.
well, you
It's
know,
just not, because it's type B is responding to alkalosis. It's not even
Okay.
Yeah.
responding to acidosis.
Gotcha.
so
Which
we're
is-
fine. Okay,
We
we're
are
fine
now. Thank you so much.
But without doing this, because I don't want to do this, I want you to actually do this one, because you can always do. You can see that what we're doing. Then you see how that's going to affect potassium levels, right? Okay, and then you're going to see when you go into that. Okay, and to affect the acidosis, we're going to increase or decrease respiration, and then to affect the hypoaldosteronemia, whichever you choose, aldosterone will go up or down, and then if aldosterone goes up and down, we expect an increase or drop in blood pressure, increase in neuropathic urine. So I'm literally taking you through what we did before of like step by step by step. And so you kind of do it like that probably on the side, but you're not going to have to worry about like which one to do first or something. You're going to see what we're doing, right? This is responding to metabolic, okay? We have the principal cells responding to the hyperarchiclemia. Then of course, since we're doing aldosterone, we're going to have an effect upon blood pressure and urine output, right? So if that's how the questions are going to be.
I was just wondering, in the last principal cell, this is when ALD is present, or like so?
Well, yeah, we always remember we never have off and on, but right. So we have when we're talking about a given level of aldosterone, that's what it's doing. It's reabsorbing sodium and getting rid of the right amount of potassium.
Right, and you were saying that the more LDH, the more salt, the salt you and water.
The more aldosterone?
Yeah.
Yeah, that
the more
means
that gets reabsorbed.
right.
Or,
Yeah,
reabsorbed,
and the more potassium gets excreted, right?
Yeah, and so like if you had less, obviously it would be the reverse.
Yes, exactly.
I was wondering, for when you did the low blood pressure before all this?
With all this, yeah.
Yeah. Does it also go to that Renin?
We're not going to go there.
Okay.
Yeah.
Okay, so the ALD is not from that. It's just from the intercalary.
It depends on where I start. I don't know what you mean. If I
Because low blood pressure on here would also move up aldosterone?
yes, but we're not dealing with the renin at all. We're sort of just saying because all we're dealing with right now are the principal cells.
Well, I was
We're
just
not dealing with
wondering
ADH.
So for low blood pressure, if this is part of it, then would ADH also go down?
But we're not doing ADH. For low blood pressure, the response is going to be what? We're going to increase aldosterone and increase ADH.
Okay.
Well-
And we just won't tell us.
But we're not going to talk about, you need to know that for this other stuff. But for these problems, you're not going to see ADH at all. All you're going to see is what we have up here in those 4 things. So, when we do these other questions, blah, blah, blood pressure and all that, I'll have renin and A and P will be that other chart. But for this one, I'm never going to have ADH as part of the mix. I'm only going to have, aldosterone, acidosis, alkalosis, potassium, and respiration. So, doable, right?
Easy.
It's almost too easy. No, don't say that. But the worst part is like reversing it, and you're gonna come back and like, I knew that and I put the wrong one. So practice doing this so that you'll do it on the side and get it. But yeah, I think people, especially if you take the time, it's really hard stuff. But if you take the time now, you guys, I told you at the beginning, right? You're gonna get smarter and smarter and smarter. If you throw this stuff the first couple of weeks, you'd be like out of here like in a second. Like there's no way you're gonna get this. And I know everybody here that's still doing it actually gets this. It's just whether you make a mistake on the test or not. Yeah.
Will you be in your office hours on Monday?
4 o'clock.
4 o'clock?
So I'm coming here. So I'm here 4 to 10 on Monday, basically.
You said you always have all the tests on you, right?
Yeah, all the tests are there. You can always look at all the old tests, and especially if you're going to take the cumulative, you can look at test 1 through 4 and get an idea of it as well. Yes.
So when you're talking about these 3 cells,
Mhm.
and you went through all the scenarios like low blood pressure, hyperkalemia, bronchi, in all the scenarios, it's a combination of either type A or type B plus the principal cell
Right.
reaction. So is it safe to say that in all of them, it's going to be a combination of those?
It's all of them.
Always.
Yeah, because the commonality there is potassium, and they both respond to potassium, right? So you're always going to involve one of those, and the principal cell, always, and something with respiration, okay? But these involve, blood pressure and potassium is also involved in this. But right, one of those, and you're going to be basically doing something with respiration as well. That's why all 4 of them, whatever we had up there, blood pressure, potassium levels, pH, and respiration, all will be involved once.
Why is high blood pressure way more potentially fatal than chronic high blood pressure?
Because high blood pressure, you can eventually cause damage, but you're not going to die from it. If your blood pressure drops too low,
Your heart.
yeah, and your brain won't get blood, and
Yeah.
and you start losing blood right away. So we try to really compensate, because and all your cells will become hypoxic because you're not getting enough blood flow, that type of stuff. So
Yeah, I don't know if I mentioned this before, but it was crazy. My grandma's in home, and I think she wasn't feeling well, and they monitored her blood, and they detected low potassium, and they took her to the emergency room right away. I think because she had like low levels of, or like low blood pressure more than anything. But what I was really surprised is all they did for her was give her like potassium, caplets.
right,
But they weren't even in, like, because I was looking up how many milligrams, whatever, and what they gave her versus like in banana and
Yeah,
more
yeah,
potassium.
yeah.
And it wasn't even an equivalent of a banana, which
Yeah.
was crazy to me.
But the thing is, you eat a banana, but how much do you absorb of the
Oh, okay.
potassium versus putting it directly into you?
So if you're taking something like that, then that's going to directly go into your stomach and be reabsorbed.
It's going to be easier reabsorbed than actually from food.
Because I was like, how could something like that? Like they were so serious, like worried about her, and she was okay. But I mean, obviously because of her low blood pressure, they wanted to fix it right away, and that's how they fixed it. And I guess that answers.
But you can also see the idea of, there's some boron here, that you understand like why this potassium came involved, right? Even though we're doing blood pressure, because you can actually see it's involved. And actually you probably could start to figure out and look at how they were related.
And so yeah, like just wondering that, like if they gave her more potassium, then that's gonna make ALD go down. It's gonna make you keep in water, and then it's gonna higher your blood pressure.
See, the idea was, like let's say if you have, yeah, I mean you're probably saying it the right way. I have to think about it. I mean, I
But
was
it
like,
starts from that is what they were saying, like, so, yeah, like if you have higher levels of LDH, or
so did she have high or low
she had
potassium?
low potassium and low blood pressure, does that not make sense?
Well, I don't know. I have to look at it. I mean, if you
I
just,
mean, yeah, I get it.
yeah, I mean, because then you have to start piecing together what was the cause and what was the effect. Because if you just look at low blood pressure from that, you would expect hyperkalemia potentially, right? If you were losing too much sodium in water to lower your blood pressure, if something was affecting that, you would maybe expect hyperkalemia. But you had hypokalemia,
Yeah.
okay?
Maybe they weren't too worried about her blood pressure, maybe they were just worried that she had hypokalemia.
Could be, because again, remember, even though this is the idea. Like my tests are hard and all that. If you look at, because I've looked at some of these questions in some of these advanced nursing, what they'll be doing is they'll be talking not about hyperkalemia, but the symptomology from it. Like you'll be looking at this thing and it'll be depressed nerve function or neuromuscular function. And you're like, and you got to remember we did at the beginning that hyperkalemia affected action potentials and all that. So they're taking you a step, and I'm looking at a couple of things. I don't know. They're taking you 2 steps further than I am, and that's why whether you like it or not, that's why I'm doing this. Because I've seen these other tests, and there's also MCATs and all that they're taking you here, the next step, and then the next step beyond. And you've got to just realize, you can't complain about the TEAS test. Like that's a bad question. You can't go up and do anything. It's like that. The questions are the questions. So they take you through that, and they just go to the symptomology. And I don't even know all the symptomology. So what can I say?
We do high blood pressure.
Yes.
She had her hand up, and then you do it. Yeah.
I know in the quiz, we had a few questions about from the immune system chapter. In the exam, will we also see some of the stuff
Nope.
that we didn't cover?
So this is just 17, 18, 19, 20. The only thing you're going to see that maybe was on there is a couple of those respiratory problems, and as far as I think on that, there's no blood typing, there's no immune stuff at all. That was all lab or done. Okay, so we're not. This is simply respiratory and kidney. 17, 18, 19, and 20. With of course 20 being today. What a day this was, right? 20 being the big guy here. Okay, and again, of course I'm still here, but also Monday, 6 hours doing everything, from what you need to practice. But everyone that stayed knows exactly what to practice, okay? And we can do another one. You want high blood pressure?
Yes.
Sure. Not here.
Can I ask a quick question for you?
Sure.
Say, but, like the last 3 questions on your lab exam had to do with anaerobic and aerobic. I think quite a few people are a little bit confused about that one. Is that going to be on the test?
Nope.
Okay.
That was lab test that when we did the ECG lab and exercise, that were the last couple pages. Nope.
Okay.
So that was that. So we have to make sure we have this now, because I need this. So type A, type B, we did that right. Here's the aldosterone ones. Again, I read for all this. Sodium, reabsorption, water reabsorption, losing potassium. Ready? So, take me through this. You have high blood pressure. What's the first thing you're going to write down?
Decrease alt AL whatever. AD.
Correct. Because, again, remember, we're not dealing with writing all that. We're only dealing with on here. The only one involved in blood pressure is this. We want to decrease that because we're going to do what? By decreasing it, what are the 2 effects? Again, what are we going to do? We're going to excrete the sodium and H2O. Okay? And again, that's going to basically, also, that will correct the blood pressure. So again, that's going to lower the blood pressure and of course also increase urine, because where salt goes. So we've corrected the blood pressure, right? We tried to. Now what else is happening though? And therefore causing, yep. So we reabsorb more potassium than we had wanted, and that potentially causes hyperkalemia. You see how this is so, it's almost too easy in a way when you have the system. Okay, you have hyperkalemia. What's your next line of reasoning?
Type B. Low, right? Or do you say hyper?
It's hyper, right? We have too much. Because we reabsorb it.
Yeah.
So who responds?
Type B.
Type B, because we want to get rid of it? Let's do that. Type B responds. So that, as you can look at over there, we're going to secrete or excrete. I'll just put go ahead excrete. Keep changing it. We're going to excrete what we have here. We're going to excrete the potassium, and bicarbonate, but potassium will carry on this. And by excreting that, we've taken care of the hyperkalemia, right? This caused too much potassium. Now we get rid of it, but what are we reabsorbing? Causing metabolic acidosis. So, we had high blood pressure. We needed to reverse it or try to reverse it. We decreased aldosterone so that we got rid of sodium in water to help lower the blood pressure, but we reabsorbed potassium, potentially having hyperkalemia. Okay, we know that these cells also respond to potassium levels. If we have too much, we want to get rid of it, so we activate type B cells. That gets rid of the potassium, but in so doing also reabsorbs hydrogen and causes metabolic acidosis. But we're not done yet, are we? What are we going to do now?
Increase respiration.
And now we're done. We increase respiration. I love when people get this. That's why I smile. When people get this stuff, I'm like so happy, okay? Increase respiration to blow out the acid, and then we're done. And we've involved all four systems. We've involved blood pressure, we've involved potassium levels, we've involved pH balance, and we've involved respiration as promised with the money back guarantee. And I really don't want to pay anybody any money back, okay?
Can you slowly, I know this is really obvious, but when you pointed to each section, we have the pH, we have this, we have the that. Can you do that a little bit slower so?
Okay, and let's put it, remember we had this thing, we had blood pressure, we had sort of potassium levels, so I'll just put potassium, we have pH levels, which is acid base, and we had respiratory, correct? Is that correct?
Yes.
Okay, so here, we started with BP, we always start with one of them, right? And so there's our BP, okay? And we corrected it by decreasing aldosterone, and then we reversed it. But at the same time, what did we do? We reabsorbed potassium. There's potassium. Okay? Type B responded to restore to get rid of the potassium, but what did it do in return? Caused metabolic acidosis, pH. Who responded to that? Respiratory. This is so cool. This was just a couple years ago. This came to me in a dream, okay? No one else teaches it this way, I promise you. And somehow a couple years ago, I'm like, it was like a light bulb. I'm like, wow, this is cool. If this does that, now it makes sense. And then I started looking up drug interactions, and you'd see these metabolic, and I'm like, yes, that makes sense. And so that's why I like this. And I love when people get it. I love when people out here, because in the cardio section, everyone's like, I don't know what's going on and stuff. And this section, literally, for the people that hang in there, it all sort of comes together. This is the peak of the course. Last section, there's some cool stuff, but the lectures, I almost have half lectures. It's a lot easier. Test is so hard, but less material. That's why 1 week from today, you take this test, you're done by now, and all you're thinking about is Thanksgiving. And what are you thinking about this class? Nothing. Nothing. There's no homework. Literally, we start fresh after Thanksgiving to finish up the last section. You all have like A+ on the test, and you can all be happy while you're eating turkey. I really want and expect higher grades. this time on this class. Usually, this class leads the A's. Now, this last one, it really started to drop, okay? And so, these other classes started getting higher A's, and I'm like, whoa, what's happening with City? Because usually City is leading. And so, I really want the A's to pop back up here, okay? Because I know there's plenty of A students here, plus B's as well. And C's move up. You know, people actually, what happened is some of the A's moved down, but some of the C's and stuff kind of moved up. So we sort of squished it, which is good. I care about the people that sort of really struggling, that they actually got that on the hardest test. I was like, I've actually had someone who went from a C to a B to an A in this class. I don't know if it's any of you guys or not. I was like, and, you know, and the test got harder. I was like, wow, whatever you're doing really right. So, but anyway, I do really want, not only do I want better grades, but I actually like that you understand. You're going to know, everyone, even if you don't do the tests, everyone leaves this class just learning a ton from today. Okay, I'm so hyped up on this day, it's not even funny. And we can do the whole thing. The only trouble is we got that respiratory stuff, okay, that we've got to still deal with on the test. I should just like eliminate respiratory system and just do the kidney, anyway. Too late now.
What,
Next semester.
Let's not really have one more review. You can say, you know what, you guys, or the email. You can email.
Blackmail.
Why again does the formula filtration
Because we have two control. Well, you can see why it's important to have it happen, right?
Huh?
You see why it's important.
Yeah.
Okay. So the two controls. Actually, well, let me just put that up there a second too, just because instead of me drawing some bad drawing. What am I doing? Wrong chapter. But feel good. All right, 19.
Well, not really like that. Yeah.
Okay. But here's the key. I just want to put this in before we do it. So, you know, we want to control GFR, just like we want to control blood flow into tissues, even though the blood pressure, this is crazy high actually, the blood pressure might be rising. So we have two main local ways, which is all I care about to do that. And it's the following. That we have blood coming in through the afferent, okay, arterial, and then of course, here is controlling the GFR. How much pressure is here is controlling what gets in, okay? And so what's going to really control it is this guy right up here. So the idea is two basic things, and here's sort of the most important one that we'll put it. This is like what we did in the cardio. That when we did cardio, we said that if increased flow went into a systemic arterial and stretched a smooth muscle, it was going to constrict, to control flow. This is the same thing. The afferent arterioles are smooth muscles, so it's called the myogenic response. So as that blood pressure is rising out here, and it's increasing here, this is going to respond by constricting, and therefore controlling pressure. So instead of allowing that pressure in, it literally will constrict it, and that pressure should remain constant. Okay? That's one of them. That's a really important one. The other one is a little weird one. You got to know this, so it sort of helps, is this idea of, and let's just look at it here, the JG response. Okay? And the idea that was that, and let me show the easy picture. That when we look at the catchal tubule of the kidney, we see that here's sort of the glomerular filtration of Bowman's capsule, proximal tubule, descending loop. The ascending loop actually passes right in between the afferent and the efferent, and cells of the ascending loop called the macula densa sense salt flow. Okay? So it kind of goes here. So if some of the blood pressure increasing and it kind of counteracts this, you know, we don't quite compensate enough by the myogenic, that means the GFR is going to increase a bit, but as it's passing through the macula densa, which is part of the actual ascending limb, that's like a question, you know, macula densa is, it's part of the ascending limb, it senses salt, it's going to send message to the granular cells, which are going to send message to the afferent arterial to constrict, therefore decrease pressure and decrease GFR. So it's another local response. Again, the other picture of this to show it, and it has the words on your handout, is this. So again, the macula densa is part of the afferent. So as for some reason that pressure or something else is called GFR to increase, it sends, we don't care about what they are, it sends signals to these granular cells, which actually make run into, which then signals to the afferent arteriole to constrict and therefore decrease. And those are the two ways that we sort of control it. Because we don't care. I think I have systemic and stuff. Don't even discuss it out and stuff. Because I'm like, we already covered H2 in the next section anyway, so nothing on this to be tested.
Do we need to know anything about the renal pressure? The diabetes?
No, only. Let's go to where are we here? Is that further? Yeah. Or is it back? No, it's further. So also, why are we doing this? So you don't even. I showed the steps of the proximal tubular reabsorption where you transport sodium and that attracts the negative, that attracts the water, that concentrates. Don't worry about the specifics. Just know bulk reabsorption. As far as again, skip this right now. So as far as the glucose, the idea is we're going to use these glucose transporters. We get that in. So the idea is under normal conditions. So you're not going to have to actually know the curve. Under normal conditions, that the amount of glucose that gets in are going to be successfully transported and done in the urine. So you don't need to know sort of the specifics of like this chart. But the idea is that if you have something like diabetes and you have too much glucose, those transporters get saturated. It can't reabsorb anymore. So what's going to happen to this excess glucose? It's going to go to the urine and be glucosuria. So specifics of like this curve and stuff, no. Just realize in diabetes, the idea is the receptors in the proximal tubule get saturated. That means we can't get rid of it all, reabsorb it all. Goes into the urine. We call that glucosuria. And of course, who's going to follow that? Water. Okay, and that's why you have excessive urination and thirst.
Does the glucose in the urine affect osmolarity, like the Jaeger parameter, or is it?
Yeah. So we're not going to talk about it.
No.
If you think we've hit the most of the kidney, nah. Okay, this is not baby kidney. This is sort of like toddler kidney. Okay, and because all this stuff is going to affect it, and we're going to affect aldosterone and all that kind of stuff as an effect to the osmolarity, because that's so actually it does is going to affect some of that.
That's
think
what they
so.
check for kidney functions when they give you when you have diabetes, right?
Right. So that's why, the kidney is able to monitor a lot. And you'll also see that's why you're going to look at acidosis and even potassium levels for diabetes, and that's sort of where we're not like heading in a way. But you can kind of see from what we did of how they would be, somehow involved. But we won't do that.
How do we get glucose in the urine?
If you look at, if we just sort of show a simple diagram again of the tubule here, let's just kind of get us. So again, everything, all the transporters for glucose and the amino acids. The only difference between the glucose transporters and the amino acids are that we always use the sodium potassium pump to create low sodium, and now we have co-transporters that in this case transport glucose and sodium. But the amino acids will have amino acid and sodium, right? Now we'll have a different one. But all the amino acids normally and all the glucose are transported here. But if you look at these, look what has to happen. Okay, you've got glucose and these guys are going, right? Or really, this sets it up and then it's like this. If you have too much glucose, okay, if we had the right amount of glucose, we're going to absorb that amount, right? Because those transporters are going. But what if you have diabetes and now all of a sudden entering the tubules, there's too much glucose? Now these guys are going to go as fast as they can, but they become saturated. They can't transport it fast enough. You got so much in, they're transporting as much as they can, but some of it's not getting transported in because we just don't have enough transporters. So we'll get some of it in, but some of it's not going to be able to get in. And once we pass the proximal tubule, there are really no more glucose transporters. Sugar goes out.
Because of no aqua and orange?
No.
Oh.
This is sugar.
Okay.
That's all water.
Water.
Okay? And water is going to follow the sugar just because water follows pretty much anything, right? Water follows proteins, water follows salts, water follows sugar as well. Because it isn't, sugar does increase the osmolarity. That is what it's doing. It's affecting the osmolarity within this solute. And therefore, other things are going to happen as well. But overall, anything that's increasing, this is why diuretics work when you look at it. It's anything increasing salt or sugar, or if you have some sort of defect in the, and you have some sort of infection in which proteins are getting in here past the barrier, guess what else is going to happen? Water. And so you're going to have excessive urination on that as well. So water definitely goes to where everything is. So again, that's really all you have to know about that. And this, by the way, this clearance thing, I don't know if I said, yeah. We're not going to need, I talked about clearance and that thing at the end of chapter 19 for the people that stayed, but it doesn't matter because I'm not going to put them on the test. No clearance. So if you just go back, let me actually just quickly just glance through this. What you need to know from this chapter, 19, because 20 is what we did today, big time, right? Like totally big time. You guys are pros, man. I'm very impressed. Again, we already just introduced this to everything, so it's really not, I'm not, you got to know all the parts, but I mean, besides that. So really we talked about filtration and proximal tubule. Again, for filtration, really all of this, you just have to realize that proteins and cells don't make it in. Okay? So a lot of pictures to say that. We're not memorizing any of that we don't know. I could put easy questions like that on, I might. 100 milliliters per day, 60 times a day, I might put those on, I'll see. Just because it's cool numbers. But here's the key. Here's the first thing, right? You've got to remember this. You've got to remember the three pressures. And we did an example already with the liver thing, right or not? Did we do this one? Or this was Palomar this morning? Did I actually practice this one again or not? No? Yes. Yes? Today?
Today?
Oh, I did in the lab, okay? And I can repeat this too. But you need to know the three forces. And again, if you look at these three forces controlling GFR, it's the hydrostatic, yeah. I have 5:45 a.m. days like this too. Okay, so I've got to hang on a second. And I'm old as the hills. Okay, this is the thing. It's like I'm gonna be like, okay, three pressures, Ed. Okay, three pressures. Okay, we have hydrostatic pressure, which is blood pressure basically in the glomerulus. That's what's pushing it through those pores. Okay, you don't need to know numbers, but that's pushing it in. But we have two opposing forces to try to equalize. One is the fluid pressure, because we have fluid in here, right? Any fluid is sort of opposing that. But the other fun one, and I don't know why it's pi, is colon osmotic pressure. We said proteins don't make it in. And basically, all the water in here says, I like proteins. And that's colon osmotic pressure. So the proteins, and who makes the proteins? Liver. Liver makes all those proteins that are in the serum. So those proteins attract the water back, and we call that colon osmotic pressure. Normally, if you add these up, there's a net filtration pressure that causes the GFR. So this beats those two. And you don't need to know a specific number. Does that make sense? Just the three pressures. You need to know them. Okay?
Hydrostatic beats the two opposing?
Yeah, under normal conditions. And that's why we have a net pressure here, which causes that GFR of 100 milliliters per day or whatever it is. You don't need to remember these numbers. Okay? Yeah.
So since that beats the other two, that doesn't mean those two don't work anymore.
Oh God, no! Because
Okay.
they're important. We'll actually break one right now. In other words, all three of those forces are controlling the GFR. You've got this pushing in, but these forces are important to oppose it to get the right amount. Okay, and that's why the famous example that I love having is liver failure. Okay, we're done with this part of the kidney. Let's just work this. See if this makes sense. This again would be a critical thinking question, but that we've started to think already on it. So, how to start working these critical thinking. So if we have liver failure, to do these questions, because my answers could have all kinds of things, you do it step by step. Obviously, if my answers have something with GFR and stuff, you kind of know where we are, right? We're on this. And so, first of all, liver failure means what? Directly. And we call that hypoproteinemia. Because this was also on the other test, right? We did that. So hypoproteinemia. Again, Don't say no proteins, say fewer than less proteins. Okay, we're not completely dead yet. The liver is beginning to fail, and so we're having less proteins. So the next thing to think of is, what pressure is that affecting? And what is it doing to it? Okay, the colon osmotic pressure is proteins attracting it back. Don't have enough proteins, we are decreasing the colloid osmotic pressure. So remember, look at my visual up here. Blood pressure is pushing it in, proteins are driving it back, there are less proteins driving it back. What happens to GFR? And that's probably the answer. So it's hard sometimes. You have liver failure. You're looking at high or low GFR. You know, again, you want to look at these because it's going to cause. Remember how I did it? It could cause hyperproteinemia, and and it's going to be combinations. If you just work it out this way, your answer, the answer there is written to the side. That's the key to these multiple choice questions, right? Is that I'm always asking something I know that we would basically know, but I want you to reason it out step by step. And so the final answer might be that, but everyone's sort of getting that. And again, I think I was doing Palomar today. Think of these visuals. And sometimes how people do this. They'll be like doing that. Anything that helps you remember. Okay, I always like hold my breath. People actually remember that. I'll see people out there sort of holding their breath to remember hypoventilating for to conserve acid. Okay, think of these poles or something too, and you'll get it. So that's that. So you need to know the three forces and how to play with it. And then I've already done that with you. The next thing is those two local controls. Myogenic response, which we just did, and the juxtaglomeralar response. Pretty much, that's it. You don't need to know all these slides. Again, all you need to know is bulk reabsorption and what we just said about glucose. And we don't need to know clearance. So that's it. Chapter 19, baby kidney, introducing us to it, talking about filtration mainly, right? That was the main thing we talked about. And bulk reabsorption, that's it. So don't worry about all this if you're not in class, you don't realize. I mean, you don't have to know how to pee exactly from that. So that's it. That's why, and I put that. That's why too, because people had to leave too, and I don't think that. I mean, if you have to leave and you couldn't see the end, it sort of sucks. I want to make sure you saw that's all we're going to cover, and then I said today, and we can do it too. So you didn't even last time. People that didn't stay this time missed a little bit, but what can you say? We're going to repeat that at the beginning, but you guys at least have the ability to say, hey, you got everything, and you can really practice and practice and practice. So it is, I admire you people a lot. Okay, I do. The people that stay and do this, you don't, I know, your lives are not like, I'm just sort of eating candy and I don't think I'll come to class. Okay, everyone's really busy, but, you're dedicated, and I appreciate dedication. So that's 19. And then 20 we did today. We did the entire 20 today. But you got to go back and do the respiratory. We did some of 17 today too. But hemoglobin saturation curves. You've got to be able to do those and understand those. El Diablo and Friends. El Diablo and Friends.
Question, could we do the hypokalemia with the intercalated cells? I already did it, but I want to make sure it's right. Hypokalemia.
I think you said that.
Okay.
Thank you for after I erased it.
I don't want to hog. I can be a hog, and I'm trying to be sensitive.
Well, in that line of things, what else? You guys are still. What else are you going to want to do tonight? Do you want to do respiratory? Obviously, we'd say yes or no. I don't know what people say. So, because we're going to do another one of those. Is that?
Can we finish all the opposing ones to those? Which would be hypokalemia.
Well, I don't know. Hang on. Okay, I'm not sure about that. We can't. Then I want to see what other people want to do.
Well, just question. You said you did El Diablo today. Is that
No.
No?
Today, no. Were you here for the oxygen, for the hemoglobin saturation curves?
When was that?
Chapter, I don't know the date. Chapter 18. We did oxygen transport, we did CO2 transport, and we did the hemoglobin saturation curves. What they did in the 5 shifts.
I think I need to see some of those to begin with.
Okay, we'll do that, if you say. Okay? So we'll do that, let's do that next, because those things we can go on.
That was the Monday the 4th we did that.
Oh, remember too, have you been on his website or his YouTube?
Yes, I have.
Okay, so you can hear that lecture, but guess what? You can hear it right now. Okay?
And get the drawings, you can get the drawings.
That's right. So again, I kind of want to do that because again, you can practice on that. And the hard thing we haven't done tonight, and that will help you out as well as anybody else who stays, is to do El Diablo, and so or whatever that is. So let's go to 18. Okay, and this helps me breathe as I erase the board, so we'll just keep it there for a second. So we're going to do El Diablo. Let's just look at a couple of these. Again, you got, overall, you get the idea. It was just diffusion, and we showed how this happened and what it showed in the chapter. All this stuff, remember, was really just to indicate this, that carbon dioxide is much more soluble than oxygen. Oxygen is going to have to use hemoglobin as a carrier. That's all that was. And we showed sort of this thing, which is not memorizing, so we kind of go through that. We could go down there. You got to know these, remember? Were you here for that?
Yeah.
Okay. And we're back. So, and I'm not going to repeat this right here. Oxygen transport is simply, when it comes down to it, we're loading it up, we're diffusing, binding the hemoglobin. Right? That's loading. Unloading, don't worry about that. It sort of reverses, but we're basically going the opposite way. So you can see it's not that much on that. Now comes the fun. And hemoglobin is fun. By the way, carbon monoxide is bad. So there is all that. So let me get to the idea of this. So the way to do this, at least, well, you don't have to do this way. The way I teach it is you do it step by step. Again, hemoglobin saturation is the fact of hemoglobin, when fully saturated, can bind how many? 4 molecules of oxygen. And so there's the hemoglobin saturation curve is the idea of, is it 100% saturated or less? 100% saturated would be all the molecules have 4. But the real key is, and we'll sort of draw it, is sort of, if you sort of put this in the cell, which it is, a red blood cell, the overall idea is that the more oxygen that is around the hemoglobin molecule, that is free out there, is going to be the more that will bind, the higher the saturation. Okay, that's the general idea. So when you're doing the curve, you've got the following. Get to rate this here. You sort of, again, it's not going to be an essay, I'm going to basically put the curves on, but sort of just to get the idea, that the y-axis is the percent of hemoglobin saturation with oxygen. So percent, saturation. Again, it's up to 100%, and since this is in a test tube, not in our body right now from this, it's down to 0, right? So it could be 0, 25%, 50, 75%. That's saying, when you look at all the hemoglobin, how saturated is it with oxygen? When you look at that. This is saying, as I said before, that saturation level is dependent upon how much oxygen is around it. And so we'll draw it from 0 up to 100 millimeters, bless you, of oxygen. Now, if you look at 40, seems to be a big one here. 40 millimeters of mercury, and that's because that this curve is saying if you put hemoglobin in a test tube and expose it to all these concentrations, you're going to see a curve like that. But our body doesn't have all of this, right? So you want to have a couple markers of biological significance. And so by doing this, again, we have this curve that looks like this. And so the way this is what Stu taught me again. You other teachers, you'll teach about cooperativity and all this stuff over here, but we're not. We're going to read it Hebrew style, okay? And which was really cool. That's why Stu is great, okay? If you get any, too bad you have me. He's so good. But he's going to read it in Hebrew style because we really want to get physiological significances. And so the idea is sort of at 100 millimeters of mercury, that is the amount of oxygen that hemoglobin is being exposed to in the lungs. Okay, when you look back at that. And what is it doing? It is loading up with oxygen, almost 100%. That's why when we're doing this, we start off with drawing it like this, okay, for our mind. We're looking at two things. We're looking at, two parts of this. What is happening and what is sort of the significance of it being the shape it is, in this case a plateau. Okay, that's why, let's go back on this. So if you look at this again, we have this idea that this area here, which is here, we're calling it the loading phase because that is where it's loading up with oxygen. Okay, as hemoglobin passes through, it's being exposed to that. Hemoglobin's really, really good, sucks it up almost 100% saturated. That's how good that molecule is. It's a cool molecule. So again, you sort of have this idea that one is, again, loading phase, because this is where it's, again, I'm just sort of scribbling a little bit, but loading, unlike usual, loading with oxygen, because that's where it is. Now the other aspect is okay, it's loading here, why is it like this? Why is it good that it's actually a plateau? Let's say you you have a blockage or you're climbing Everest and you don't have that much oxygen. Let's say you only have this much. You want only half your hemoglobin to be saturated. Wouldn't it be nice if we're almost fully saturated? Okay? Luckily for us, that's how hemoglobin is working. So that's what I kind of write sort of the purpose or the advantage, let's say, of it being a plateau is that even at lower concentrations that you might be exposed to, it basically still can become almost fully saturated. So those are the two things I want you to remember about starting over here. It's going to be the loading phase where the hemoglobin is loading up with oxygen, and this is the other bullet point. The advantage, or whatever you want to say of being a plateau is less than ideal conditions still can be pretty fully saturated. And it's sort of on there. The second one is, now we look at this. And that's why we like to do it this way first. Because we load it up, but what do we want to do? We want to unload it, right? We don't want this thing to hang on and just keep to it. We want to unload it. And so if you look at the concentration of oxygen in a resting cell, one that's only semi-metabolically active, it's at 40. And so you look at this and you're like, okay, it's about 75% saturated. And for me that means it released about 25% to the cells. Because that's how I like to think, right? Because I'm not chemistry, I'm biology. And so the idea is, and then this is what confuses people too. 70s, nothing's happening here. Our lungs we have 100, and then it's going through the circulatory system, hanging on really, but this is where it's being exposed to that. And what it's going to do is unload about 25%. We don't want to unload all of it, because if we're more metabolically active, we're going to have less and less oxygen. We want to basically unload more. So those are the 2 points here. The point is that it is this is the unloading phase, which you can see we're unloading to the tissues. The advantage of it being steep is that if we're a plateau and we need more oxygen, it would say, forget it, I'm holding on to it. We see that it's responsive to the needs of the tissue. The more oxygen you need, because we need more, the more it's going to release. If we are exercising and only have, let's say, 30 millimeters of oxygen there, we have something like 60% bound, so released 40%. Okay? And so it's going to keep going that way. It's going to be responsive to the needs of the tissue. And that's sort of the first steps of the hemoglobin saturation curve. What's happening here and why? What's happening here and why? Does that make sense?
Yes.
Okay. Now the fun. There's all these shifts. Okay? And this is kind of, I just put this in just because, again, I'm going to kind of put this. In order to figure out the shifts, we can just put this up here. You're going to have, what you're going to have on this test will be, 3 curves, like one of these. Except I'll have this kind of, covered up as far as that goes. And basically, in order to do this, it's actually pretty easy. Okay, but here, if you have a trick. And here's my trick. Don't even worry about that at all. So you have 3 curves, and what that means is different conditions in the body is going to cause the hemoglobin to work a little differently. So it's going to shift. The whole curve kind of looks the same, but it shifts to the right or the left. All you have to remember is this: a shift to the right, and we'll show you again why. A shift to the right of this means that hemoglobin has less affinity for O2. Which means what? Is it going to release more or less? More. Less affinity means it's going to release more. So a shift to the right means it's going to release more oxygen compared to where it was in the middle. Okay? As long as you remember that, for all these shifts, all you have to remember is, it's going to make, if we're alive, things are going to make sense. Anytime we need more oxygen, it's going to shift to the right. Okay? So instead of memorizing those things, which of course you always can, I sort of do it this way. Let's just think about high metabolism. We're running or active. If we have high metabolism, overall, what are our gases going to be? Low 2 and high CO2. And so high metabolism, are we going to want the hemoglobin to release more O2? Yes. So we're going to shift to the right. Okay? And let me show you that too. By the way, if you didn't believe me.
Wait, can you just ask that one more time?
I will, and I'll show it up here too. But, well, first of all, if you remember, a shift to the right means what? Is it going to release more or less oxygen? Okay. If you're exercising, or whatever, high metabolism, you're decreasing the amount of oxygen in your body and building up CO2. Under these conditions, which way do you think you want it to shift? Yeah, and it will. Okay? Because that means it's going to release more oxygen. So conditions associated with this are going to be the one shift to the right. Just to show you that it really does, especially in case you came in because you don't believe it, because you make mistakes, Mike, don't have to go there. Let me show you, don't even worry about that, but let's show you the shift to the right always does. If you look at 40 again, and we went to the middle one, remember 75% saturated, or at least about 25%. If you look at the curve to the right, what do we have? 60% saturated, it released 40% more. So if you do that every time, you're going to see it does release more, which is what we're saying here. Okay? So, high metabolism. So, low O2, high CO2. Okay? Now, how about temperature? High metabolism is what? Low or high temperature? High temperature. Okay? Now, one more thing on this. Let me put it up here. Something which is in your dreams. High CO2 is also associated with high hydrogen, right?
Yeah.
Which is what? Low pH. So, if we're right, we're saying high metabolism, we need more oxygen, we want these things to cause a shift to the right. Okay, let's see if we're right. Okay, we have, and let's do it. Let's start over here. This is one of the curves. If you look at this curve, okay, we have higher CO2 than this, right? And it shifted to the right. Higher CO2 shift to the right, and we were right. We said high temperature, shift to the right. High temperature, shift to the right. We said low pH, shift to the right. Low pH, shift to the right. So you can memorize these like separately, but I just don't think you need to. I think if you remember shift to the right always means that it's when it has less affinity, it's going to release more oxygen, that if you fit this, all this is associated with we need more oxygen. And so all those curves naturally shift to the right. What's happening is that CO2 that's building up binds the hemoglobin, causes it to change shape and release more oxygen. What happens? Hydrogen ions bind to the hemoglobin, changes its shape, allows it to release more oxygen. Temperature changes its shape, and so this is how these, just if you go basic chemistry, biochemistry, how things work. But that's sort of why it's working. That's why those are 3 of the 5 curves. We have 5 curves. Do those make sense? You can relate all those to that. And remember, am I going to throw like a hypothermia on there? Like too cold? I can, and you know I will, right? And that means shift to the left. So,
Hyper would be to the right.
Yeah, because that's high temperature. So if I do any of the reverses, you shift to the left. But, if you know right, you know that. 2 more curves.
Are
Yeah.
you going to do hyperkalemia?
No, there's no hyperkalemia here.
Okay, and maybe it's,
Yeah, I know, you gotta have it in the brain. We're going way back, we're way before hyperlimia now, we're on, last season, okay? And so, here's the fourth of the five. And this is kind of a weird one, but you can remember it however you want to remember it. If you're not getting enough oxygen, you have hypoxia for whatever reason, you've gone to a high altitude, anemia, whatever that is. And the idea is, you're not getting enough oxygen, which of course means you're gonna want this curve to shift to the right. Okay, the way this is gonna work is the following. That if you're not getting enough oxygen, you're gonna be relying more on anaerobic respiration, glycolysis, right? Because that's what you do when you don't get enough oxygen. Now, glycolysis, if any of you have done that before, has all like 10 different steps and all that. The cool thing is that, again, all these steps, one of the intermediates of all these is 2,3-diphosphoglycerate, which is 2,3-DPG. While that's also involved in glycolysis, it comes over to hemoglobin, binds to another site. That's why I'm kind of hot on hemoglobin. It's pretty cool. And 2,3-DPG will bind that, change its shape, and release more oxygen. Because we're saying, hey, we're doing our part, but this is not a time to hang on to that oxygen, right? We need it. And so it's going to cause a shift to the hemoglobin will release more of its oxygen because we're not getting enough. That sort of should make some sense. It's just that this is a weird molecule for most of us because where did this come from? You don't have to worry too much about it because it's not an essay anyway. But again, that under conditions which are not getting enough oxygen, you rely upon glycolysis. We're going to have one of those compounds come over and bind, cause a shift to the right so that hemoglobin will release more of its oxygen because we don't have enough oxygen. Okay?
so just remember that, thing,
Yeah,
okay.
just that. I know, all of our brains are like, words are almost gone, right? The fifth curve, and then we're pretty much through. I put this up, you're not going to know it, but I was going to, maybe next semester I'll do it, for carbon monoxide is a full thing, but you have to know that. So this guy, let's get the fetus. So unlike all these others, we're talking about shift to the right, chief factor, without worrying about completely why. Fetal hemoglobin in that mother is shifted to the left. And so, don't freak out on what that means. It has higher affinity, and you try to figure that out, because our brains are tired, right? You just have to know two things, kind of why. The conditions of the fetus are different than the mother. The fetus isn't being exposed to, air, right? So what's the point of having it work that way? We want to kind of get where it's picking up to where it's exposed to. Its cells are working at a slower rate, and so that's where we want to drop it off. This just fits the environment of the fetus. Okay, that's all you have to know. Shift to the left fits the environment. But you have to know why, because I have some kind of question on that, and that's up here. The reason it looks that way is whereas our hemoglobin, adult hemoglobin, maternal, has 2 alpha and 2 beta, fetal hemoglobin has gamma, it's up here, instead of beta. And so those chains just causes it to act differently and cause this kind of shape here. So gamma instead of beta makes the hemoglobin basically have a curve which is to the left of what most of ours are. And that's the 5 curves.
So all of a sudden the beta chains turn into, or rather the gamma chains turn into beta chains.
So what happens is when the baby's born, it's got to get rid of all of that hemoglobin, and that's why you can have jaundice. Because if you remember, from back in the other chapter, if you have too much hemoglobin, you get too much bilirubin, and so you can actually be jaundiced temporarily. And then once that happens, you're going to replace it with normal hemoglobin 2 alpha 2 beta. So you don't take the hemoglobin you have and replace that. You actually have to get rid of all that hemoglobin and then have the normal one with 2 alpha 2 beta. Someone else said, that's that. Okay? The only other thing in this chapter, and again, is, and you have all the steps written down as far as carbon dioxide transport. Right, and again, that's not an essay either, because I just don't feel like it being. You really just have to sort of understand, when you look at those steps, kind of what's happening there. We're diffusing, and then everything's exploiting diffusion. We'll bind some with hemoglobin. Again, hemoglobin, we already bind that carries it. That makes you recreate the concentration gradients. And then, even if you're not sick of this equation, it's in the blood cells too. CO2 plus water, we skip the intermediate, hydrogen and bicarbonate. So as CO2 comes in, we convert to these products. That drives diffusion. Another way to get that guy going is to remove the products like we've been playing today. 2 ways. Hydrogen will bind with hemoglobin. that also serves as a buffer, right? Otherwise, those hydrogen ions are going to be acidifying, but that will drive it. And then, what it's named after, the chloride shed. We're going to transport that bicarbonate out of the cell. Most of the CO2 will be transported that way. It's nice and soluble, it's a buffer, it's really cool. But by doing that, we are really driving getting rid of CO2. But we're getting rid of that negative charge. So it's called the chloride shift because chloride now will enter as bicarbonate's going out to equalize the charge. We're shifting chloride from out to in. Okay? And that's why it's named the chloride shift. The last step reverses in the lungs because everything is reversed in the lungs, so we just don't want to draw those 6 steps again, right? Because we get it, okay? Concentration third, You can actually see the transport is exactly the opposite. Bicarbonate goes in, chloride goes out. Simply don't worry about that. Simply worry about sort of what's happening here, especially this last step. Realize what we're doing here. Bicarbonate is going out, which is driving it. Chloride is coming in to equalize the charge.
The hemoglobin binds to the hydrogen, it's actually exiting the orbital.
No.
So how is it removing or switching?
Because whenever you bind one of these free things, it's like removing it from the equilibrium. So again, I don't like the way they do that.
You replace it with the Cl.
Again, if you do the low mass action, just put it out here versus having the way they have it. Okay, and we have it before. And we just play with it. If you remove hydrogen, well, any way we do it, and you can do it by just binding it up. That's removing it from this equation. And so that will drive it. So anytime you don't have to get rid of it if you bind it up. Okay, that's probably what your basic question is. So once you bind up the hemoglobin, it effectively, it affects this equation. It's no longer part of this equilibrium anymore, right? Because they're going back and forth. So that's how that drives it.
Okay.
So kind of 2 ways. You can kind of get rid of it, or you bind it up so it's no longer sort of active. And again, the only other thing in the chapter was respiratory control. And again, I've already said all you need to know. You don't need to know this crazy figure here. You just have to know the peripheral ones mainly respond to low O2. That's all out of all that. And that the central ones, and look at our friend, CO2, or since CO2 can cause acidification more than the oxygen being a problem, in our brain we have these chemoreceptors that mainly respond to CO2/hydrogen levels. You see the relationship. CO2 can diffuse through in, we have its enzyme, we start converting to the hydrogen. If we start seeing a lot of that, we're going to increase respiration. It controls exactly like we said was going to happen when we put it, that's controlling it. So central ones are responding to that. And that's all you have to know for that. So we just did check for 18 too. So we kind of went through 19, we definitely went through 20, we sort of skimmed through 18, and we've done part of 17 already too. So we've almost done the test.
Unlike sand colors.
Yes, these are pretty intense days. Usually some weird things happen around now where people start just laughing hysterically for no reason. But we've done pretty good. Okay. So
Okay. So wait, the central receptors do what again?
they'll respond.
Respond.
Response to mainly the CO2/hydrogen levels. The peripheral ones responds to not having enough oxygen. And then will increase.
So CO2 as opposed to lack of oxygen completely. Well, not completely, but lack of oxygen.
Yeah, in other words, you can see the oxygen, we've got so much buffer on that. If we lower oxygen, we say hemoglobin release more. But if we start building up CO2, what happens? We build up acid, okay, that means like acidification and death. So we've got to get rid of that. Our brain cares more about that.
One more time. I'm so sorry.
For which one?
Central receptors respond mainly to.
These guys.
Okay.
These 2 guys. So if you're not breathing enough, or your CO2 is building
And
up
hydrogen?
/ acid, right? Because they're both, we know the relationship by now from them, right? CO2 means acid to us because of that. We've got to breathe it out. It says breathe it out.
So pretty much you're saying that our U2P is more focused on carbon dioxide release than the need for oxygen.
Well, you need both, but the thing is, that will more critically do it. Like if you're holding your breath, and you've got to be that. It's not because you don't have enough oxygen. Okay, you're not becoming hypoxic that fast, and we'll just start releasing more. Look at that buffer. It's because of this. So you know, I don't wanna, you know, the way you said it, like, I don't know if I wanna say that, I mean, we need to breathe because we need oxygen, otherwise we wouldn't do it. But we sort of have, you know, this helical, we have a buffer built in where we can actually handle lower amounts of oxygen. But we cannot handle very well too much CO2 because of that acidification idea and all our proteins are acidifying. So, you know, I guess in a way, our respiration is more sensitive to our CO2 levels than necessarily the oxygen levels. But of course, we're breathing the oxygen. You know. But you can see, just as importantly or more important, is getting rid of that CO2. That's why we did it for that 7 steps. Look how much trouble we go to unload from the tissues. Okay, we go crazy amount of trouble, right?
What's that fun fact? So you might performance know about 100 meters.
The GFR, 100 milliliters a day. How many times do our blood supply goes through? 60 times a day, because we have 3 liters of fluid. I should put that fun factoid in, right? Yeah.
Yes.
Yeah.
Because it's a cool factoid, right?
You know what? You can even separate it and do 3 points.
You want too much. You
I
want
just
too
want
much. Well, you just gotta do what you've been doing today, and do it over and over and over again. Try not to confuse yourself. Sometimes you just confuse yourself. So
I think I've been doing that the entire time.
yeah,
Is what it is.
yeah. And I can't
And I
stop
always
doing
second
it.
guess. Always.
So, and I can say stop doing that, but that's not really work. So you have to just just do the best you
I'm
can.
approaching this entirely differently, which I hope isn't too late in the semester, but I'm just like, just stop what you're doing and do it this way.
Yeah. It's almost like, you know, have like a half a beer before you come in. You know, sometimes I told people, I didn't really mean it, but some people, that's what happens. It's like you're so hyped up and all that, that really, you're like, if you somehow can calm down and it's like you know the answers, but you'll start flipping otherwise. Write things down that you've been practicing. Yeah, you don't have to overthink this. You can see, it's hard enough. I mean, I'm not going to make you think more than this. It's like, if you can think of what we did, you got the test. People do better on this test, okay? Unless they've given up. People do better on this test than last one. Laugh. Last test was hard. But we, you know, I gave like 9 points, and so we have A's, B's, and all that, but it was a hard test.
So I came in late today, and so I was just looking at that picture that you drew the nephron, and you have like 300 going in with like an F and then a 300.
Filtration. We were following. Well, I don't know exactly where you came in.
I came in 20 minutes late, so I don't know.
But you
So
and
I'm
it's
just
like what
gonna
date, what minute?
backtrack on
Okay,
this
at the minute 20, where was I? Okay.
When you came in, you were or when I came in, you were talking about the vasorectal.
Oh, you're kidding me. Oh man, well you missed a big part. We gotta go back to that.
Can I just ask something really fast?
No.
Okay.
Yeah, go ahead.
I don't know if we could do this without having to write it all down, but for the hypokalemia,
you got the
I
hypokalemia
really
on the
need it,
brain.
I need it. So that type A response, right? Never mind.
It's like, wait, yeah,
You
I
don't have to
can't-
write it down, it's fine.
Yeah, let's wait a minute on that. I can't. You know, it's like I don't have that. I tell you, I don't have that in my brain. Okay, I have to like draw that. Okay.
I came in actually right as we were talking about vertical osmotic.
But did we? But you saw what happened going down and what going up. That I went through that or not?
I didn't see that.
Okay, well you're gonna see it now. Okay. So. That's because I misdirected you on that one traffic day, so I feel bad. Yeah. So, okay. So let's just again redraw this. All right. So we draw the nephron. Okay. So. What we've done up to now is the following from the last chapter. We're dealing with osmolarity now, and we're going to show sort of what we're going to do here. Bless you. And we just, sort of what I did when we were doing the beginning is realizing what the osmolarities were. That in the blood it's 300. We filter it in, it's still 300. Even after bulk reabsorption, when you're in the top of the ascending or descending limit loop of Henle, it's at 300. Because we haven't changed the osmolarity, somehow. Okay? Even though we've done all this stuff, we've literally maintained the osmolarity at 300. We haven't changed it from where it was. It's magic. Magic part 1. Okay? I don't know how you can do all that, but it doesn't. All right. Then, so again, we just do this part again. The idea of, when we go back to chapter 19, there are two types of F-lines. One is extended, is extended a little bit and goes vertical. The other one's extended the long loop of Henle, called juxtameasuring. These are the ones we're talking about now to make this gradient, to make the different concentrations of urine. This one is that feedback. Okay, that's why I want to show that picture.
So I just feel like juxtaposing.
Yeah, I guess. Those are the long guys. Okay, and this actual slide was in chapter 19 as well. I just re-put it just because visually when we're going over this, I want you to see which ones we're dealing with, because now we're about to use these before we just introduce them. Okay? And I put this up, you don't have to memorize this in a way, but this is where Stu, basically when I came in, learned about the kidney, he just wrote this up the first day, and that these long loops of Henle are going to create this vertical osmotic gradient that the collecting dut's going to use to make concentrated urine. And you're like, okay. But then we went through it. So, all this is to so, instead of showing you as we do on the board, like here's the vertical osmotic gradient, where did that come from? I just wanted you to get a visual when you look at the kidney of what we're talking about. That's why it's the juxtameasuring ones that care, because that's where the strong or the long loops generally goes. So, the deeper gradient, 1200, 900, 600, that's what the vertical osmotic gradient means. Okay? So it's vertical going from in to out. Just wanted to kind of show that. Okay. So then what you do is the following. When you're doing this, even though we're dealing with the long loops, you're literally going through each segment and saying what's happening. Okay? And we go through the descending loop. What it's doing, let's go to a bad nephron, is reabsorbing water. That's what's happening. So, if we're reabsorbing water, okay, we're starting at 300, reabsorbing water, what's happening to the concentration within the filtrate?
It increases.
It increases. You're getting rid of water. It's like evaporating the water from like a salt. So it's getting bigger and bigger. At the bottom of the loop of Henle, these long loops, it's at 1200. Because all we've done there is reabsorb water. Okay? And that's all the time, right? There's no problem here. We don't need the hormones. Water in all these segments here can always be reabsorbed. Okay? They all got aquaporins. They're all cool. Now, here's the sort of the half magic here. When we go through the ascending limb, which you can see even by the cartoon, looks completely different. It is completely different. We are going to pump or reabsorb salt. Okay? Remember, this is reabsorption, which is going into the interstitial fluid and also going back to the blood. But we're going to basically reabsorb all these ions. Sodium, potassium, our famous potassium, chloride. Okay? So we're pumping out salt here. Now, when usually, if we pump out salt, water looks and says, I want to go there. Guess what? Never. No invitation. There are no aquaporins in the ascending limb. So that means, basically, even by this cartoon, we're going to reabsorb ions, and we're going to use that to create this nice osmotic gradient. Water can't follow. So that means, if we looked at the filtrate, if we're reabsorbing salt, but water is staying in here, what's happening to the concentration within the filtrate? Right? Because we're getting rid of the salt, but the water is there. And if you look at the top of the loop, you can actually see, we started at 300. Actually, we can use this too if you don't like that. We started 300. We ended up 100. This is how much salt. So each time it passes, we are basically depositing salt, right? Because we have less here. And that's basically, again, there's a slide in which I talk about why it's vertical, okay? Like this crazy thing that you don't have to know. Because people are like, okay, I get you putting salt out there, but why is it vertical? I'm like, yeah, it's sort of complicated. We won't worry about that for this class. But if you're really interested, you can read that slide. Okay, it's cool. But the idea is, it will basically, by doing those two things, you don't have to know, this is showing you the transport proteins, but you don't have to know that. But basically, zoom, here's the inside of the ascending limb, and we're going to use all this to reabsorb all that salt. And again, I think they have a good picture. Yeah. We're literally going to use active transport and a lot of energy to do it, but it's going to be worth it. So, anyway. So it just says it here. But again, so if you look at this again before we move on, we have this idea, again, from Stu. The long loops of Henle are going to create a vertical osmotic gradient. This is going to use. How we do it. We reabsorb water only on the descending limb, making this more and more concentrated inside. On the ascending limb, we transport, reabsorb ions, salts, and then in here, that's going to help us create this gradient. But by doing it, if you look inside the filtrate, then it's getting more and more dilute. So at the top, it's at 100. Okay? Now, distal tubule. What's not listed in the book is the fact that most of the distal tubule is doing the same thing, reabsorbing salts. So that if you go to the top of the collecting duct, it's 50. It's very dilute. Now, if you look at the body, this is no matter what conditions in your body, right? All this is like set, okay, for those. But down here, it's something different. Depending upon all the things we talked about after you came in, the urine can be anywhere between 50 and 1200. And that was the whole idea that basically we had this idea that this, actually I have to go back a second too, but the long loops of Henle created the vertical osmotic gradient, and now the collecting duct is going to use that to make more or less because it's going to control by hormones. And so when we're looking at this, and I'll go back to the vasa recta, because that's a step I skipped for a second. If you look at this, again, you have this idea of, in some of the questions were actually on like this quiz, right? Because I knew you could look it up. The idea of each segment, what it does, and especially what happens with water, okay? And so here, bulk reabsorption, and clearly water has no problem, right? Plenty of aquaporins. Here, we're reabsorbing water only, so there's obviously there's no hormone, I mean it's always being reabsorbed. Here, never. I don't care. No invitation. You could throw ADH on there, it's not going to happen. No aquaporins, no water reabsorbed ever, okay? Ascending limb, most of the distal tubule. Here, hormonal control, okay? Aquaporins only with ADH, and then we'll start inserting it in. So, one thing that I skipped here is, and don't forget these words, because I already know, we'll put it on here. I think some question has this. This is where, you've got to underline words. I said the long loops of Henle created the vertical osmotic gradient, and I showed you how. But once it's created, we don't want this water, we're going to still have fluid going in. We don't want this water diluting out the gradient, or we don't want to mess with the gradient. We need something to maintain the gradient. Okay? And that's going to be the vasa recta. And again, to look at this crazy figure, this is crazy stuff. I still can't believe this stuff.
Yeah, what exactly is that?
So when we look back at even the earlier chapter, we said there were all these paratubular capillaries that things were going in. So the vasa recta are specialized, okay, and they're specialized in the sense that they are going to run counter-current. And sometimes if you do stuff with heat exchange, you might look counter-current. It's crazy stuff, right? But here's the idea of it. Here's how we just talked about the filter running, right? Now, what's going to happen in the vasa recta near this, it's running, it's coming in near this guy. So it's running counter-current to this. And look what's going to happen, how it's going to maintain the gradient. So it's coming in 300 because that's blood, right? Now, there's so much salt being pumped out, high concentration, that as it's descending next to this guy, it's picking up salt, right? Remember, we're pumping out salt out here, a lot of salt. It's next to it, it's literally picking up the salt. And as it's doing that, instead of having salt mess with this, and by doing that, it's doing what? Creating higher and higher osmolarity within the blood, within the vasa recta. So it's picking up salt on this side. And at the bottom, it's 1200. Osmolarity or salt concentration, right, within this thing. So at the bottom, just like everything's equilibrating, you kind of look out here, out here, 1200 level, 900 level, etc. So it's picking up salts on the way down because it's running the counter-current. Now look what's happening here. If you look at this thing, do we want that water, because we're always going this way, do we want that water to dilute our gradient? Okay? Answer it.
Wait.
Do we want, we're looking at this thing, right, without this vasa recta. If we didn't have this, and water was continuing to be sort of reabsorbed here, what would happen to our gradient? It's like having salt water and adding water, right? It would be gone. We don't like that. So look what we did. By the vasorector running countercurrent, picking up all that salt, what is water seeing here? Party. Not only a party, but a party back to the body. It's like a moving party. So instead of the water staying there, it gets sucked up. And remember, we're reabsorbing water in the body, which we want anyway. So basically, it picks up salt on this side, will help be a kind of a magnet to pick up the water on this side, so we won't dilute the gradient, we maintain the gradient. It's not used to create it. We do that other thing to create it. You know, the long loop of Henle, like we said. But these are going to maintain it.
It's a party bus.
It's a party bus. And that's the key words. Create versus maintain. You know, what if, okay, remember, we have this gradient. This gradient allows us to concentrate our urine, correct? Okay, what if the vasorector is not working? What's going to happen to the gradient? Are we going to be able to concentrate our urine or not? No. Okay, that's one test question right there. Okay? So, and that's sort of the idea of that, right? I think that's what you missed. And because you were here for low and high blood pressure.
Yeah.
Yeah, okay. So that covers that again.
Kind of a crude question, but you know you're not drinking enough water when your pee isn't clear. But from what I'm looking at here, that means you're drinking too much water, yes? Because you need it to concentrate.
Say that again?
You need everything to become more concentrated throughout the process of this.
This always happens no matter what.
Right.
Okay? So you're at 50. If you're not drinking enough water, okay, you're what's going to happen to your ADH?
What's the hormone
That makes.
Right.
Do you need more? You're not drinking enough water. So do you need more water?
Yes.
So are you going to excrete the water, or are you going to reabsorb it?
You want to excrete it. No, you're going to reabsorb it if you
Don't have enough, and so ADH is going to go up to reabsorb the water, and your urine's going to end up not being clear. It's going to be all concentrated, right? Okay. Remember also from this, since we're here, because I think I've said it a couple times, but now I don't even know what I'm saying anymore. But since I have it up here, thinking again, I gave you the sheet on diuretics. You don't need to know the specifics of it, but sort of all the diuretics work by working here, here, or here. By instead of reabsorbing, because remember, you reabsorb here in the loop, you reabsorb here in the distal tubule, and here you have the principal cells that can reabsorb sodium too. Right? Those are all capable of reabsorption. And that means we're reabsorbing it from the filtrate into the body. Now remember, if you want to pee, okay, if you want to increase urine output, what do you want in here? Just in general. Put it this way, if you want more urine, do you want more or less salt in the tubule?
Less salt.
You want more salt here, okay?
Because the water follows it.
Because the water follows it.
Why would you want to pee a lot?
Well, we're saying you're going to take a diuretic. You have high blood pressure. They're going to give you a pill. She was even talking, right, to actually, increase the amount of fluid that you're excreting. Right. Like if you have high blood pressure or some other things, you're going to want to, actually take a diuretic to lose that water. So the diuretics work by, in other words, if we're reabsorbing salt here, okay, in all these places, that means there's less salt here. Okay, that's less urine. So what do we want to do? We want to inhibit the reabsorption. Okay? So Lasix, which you don't have to know the name, but is a loop diuretic. When you hear loop diuretics, guess where they're working? Right here. Instead of being able to pump out of that salt, we're going to keep salt here. And that means what? More urine, right? Salt attracts it. There's other ones in the distal tubule that would do the same thing. If you inhibit salt reabsorption, salt stays here, and salt says, you're coming with me, water, we're a diuretic. There's an aldosterone receptor antagonist, okay? Again, if you look at the principal cell again, okay, we've done this a lot now, we don't have to worry about potassium, that if you have aldosterone, normally this is reabsorption of sodium. If you use an inhibitor, an antagonist, that means sodium is going into the tubules. Who's coming? Water. So those are the three classes of diuretics. But again, you don't have to like memorize that for this class. I had that for fun, for your information later. But it's working by decreasing the reabsorption of salt. That keeps it in the filtrate, and just like glucose did before, that attracts water. That's how diuretics work. Except for alcohol, which inhibits ADH, right? That's a little different. But these all are actually affecting all these transporters that we just talked about today. Crazy day. And it's actually, so we've been talking about this for like 5 hours. Okay? This is like incredible. This is like, it's incredible, isn't it?
Yes.
Right. And it's not like we just started at 5 o'clock, right? I mean, we're all up at whatever. I don't even know what. I can't remember.
You don't even want to know how
I don't want to know.
early it was up.
For me, today was a later day, and I got up at 6:15.
I was up till 4.
You
On
got
and
up at
off.
4?
On and off. I had to drive my fiance to a surgical procedure, which wasn't at 4. It was like at 9ish. But we had to leave the house around 8. He has to take like a thing at 4 in the morning. And knowing him, I would just had to be up because he probably would be falling asleep and it would have spilled everywhere. He would have messed with his prep, and then he wouldn't have been able to get his procedure done.
Right.
So I was like, the alarm I had set, I'm like, are you drinking it? Are you drinking it every 15 minutes? I babysat.
Hey. Those preps for those things suck, too.
We got good news. No precancerous polyps.
Oh, so you had the whole colonoscopy?
He's 31. Like, he shouldn't be having that.
Right.
But 3 years ago, in 2010, he had issues or whatever, so they did a colonoscopy, and they found that he had precancerous polyps. So they removed them, and now it's like recommended that every 3 years he continue. I mean, he has a history of it in his family.
He does have a history.
But this one, which was his second one since 2010, there was none, which is like a good thing.
Yeah.
So we'll see. I think that he has to do it in 4 or 5 now. But he still has, I mean, he's due for another one in 5 years, so I'll be up again. Maybe
Yeah, see, I'm supposed. I haven't had one. I'm supposed to have it at 50, and I'm not looking forward to it.
You should do it.
It's the prep that's the worst thing.
The prep is.
It's horrible.
Well, it depends. If you get there's 2 preps. If you get I don't know. You do your thing. I feel like I'm keeping you here. No.
See you
We're all dead.
Monday.
Monday.
Monday, yes.